Hi scholars, Ms. Beglin here with your Unit 1, Lesson 3, Precipitation, Double Displacement, and Net Ionic Equations async work. I couldn't really find a video online that was like short but covered everything I wanted it to, so I decided to make my own, and for the occasion, I got all dressed up. In case you didn't notice, I'm wearing a lab coat. So yeah, this is a very special occasion, and let's get started. So scholars, we have been talking a lot about solutions. We've been talking about molarity, we've been talking about what happens when you dissolve things in solutions, and the reason is because we are moving towards talking about reactions that take place in water. And these reactions are super important. I mean, just think about it. Water covers like 75% of Earth's surface, our bodies are 75% water. Solutions are all around us, in our oceans, our rivers, our streams, in our bodies. So reactions in water, sometimes called solution chemistry. Oops, I don't like red. Blue for water. Solution chemistry are incredibly important. One very common type of reaction in water that we see in chemistry classes frequently is precipitation reactions. This is when you add two seemingly normal liquids and a solid all of a sudden forms. Precipitation reactions have really important implications in environmental chemistry. They have direct uses in mining and in recycling for recovering metals from their ore or from recycled materials. They're also really important when understanding stuff like ocean acidification and what was the chemistry behind the Flint, Michigan water crisis. So precipitation reactions are really important. It's a reaction we're going to be developing our fluency in and spending a lot of time on. Let's talk about the reaction mechanism for precipitation reactions. The reaction mechanism is how a reaction occurs on a particle level. So how do individual particles actually interact to produce this thing, this chemical reaction that we see? Let's examine the reaction of barium nitrate with potassium sulfate. We can represent the initial state as two separate beakers, one containing each solution. We'll call this one our barium nitrate solution, and this one our potassium sulfate solution. We dissolve our barium nitrate and our potassium sulfate in water. And as we've learned, when ionic compounds dissolve in water, they dissociate or break apart into their cations and anions. Now we also learned when we're drawing particle diagrams, we want to label our particles so people know what we're talking about. For our barium nitrate, which of these two do you think represents the barium? Which represents the nitrate? Our barium is going to be represented by the black dots, and our nitrate is going to be represented by the light gray dots. The reason being that there are two gray dots for every one black dot, just like there are two nitrates for every one barium. And the same applies over here. This gray dot is going to be our sulfate, and this gray dot is going to be our potassium. So let's rewrite this the way it really exists in solution. We have our barium that's dissociated, our nitrates that are dissociated. I move the subscript to as a coefficient because the subscripts indicate I have two nitrates. If I were to leave it as a subscript, it would indicate that they're bonded together, and they're not. Plus 2 potassiums forms, or not forms, and 2 sulfates. Now, when we mix these all together, these ions are free to interact with each other. So our nitrates can interact with our potassiums, our baryons can interact with our sulfates, and this is where something interesting happens. Barium sulfate is an insoluble ionic compound. It doesn't dissolve in water. So when barium and sulfate connect, it forms a precipitate that settles at the bottom. So the way we can represent this is it forms barium sulfate, which is a solid, and then our potassium nitrate, or actually let me, and then our potassium and our nitrates remain dissolved in solution because potassium nitrate is soluble in water. So a lot of times the way we see these reactions represented is using a balanced chemical equation, where we indicate the aqueous compound together, even though it's really not. And that's okay. It's just easier. I mean, look at how annoying this thing is to write. So this is our chemical equation. This is our complete ionic equation, because it shows us how every species exists in solution as an ion. Scholars, you may have noticed that our nitrate and our potassium doesn't really do anything. It's aqueous before, it's aqueous after. Yeah, doesn't do much. We call these spectator ions because they do not participate in the reaction. They just hang back and watch. So we can simplify this expression by getting rid of our spectator ions. And what we end up with is a much simpler equation. And we call this our net ionic equation, because it shows us what actually happened. It shows us the net change. So scholars, you may be wondering, well, how did you know that barium sulfate was insoluble in water? We use something called the solubility rules to tell us that. These are rules for whether or not an ionic compound will be soluble in water. So I'll walk you through these. Make sure you capture them in your notes. Here we have our list of soluble ionic compounds. So group 1A ions, lithium, sodium, potassium, and ammonium ions are always soluble, no matter what chemical compound they're in. So sodium chloride is soluble because it has sodium in it. Potassium phosphate is soluble because it has potassium in it. Ammonium nitrate is soluble because it has ammonium in it. All of these are soluble always. Nitrates, acetates, and most perchlorates are soluble. So like I said, ammonium nitrate is going to be soluble, even if it didn't have the ammonium. Let's say it had calcium. It was calcium nitrate. That's going to be soluble. Magnesium acetate. That's going to be soluble. Compounds containing chloride, bromide, and iodide are soluble, except when paired with silver, lead, copper, or mercury. So magnesium chloride is soluble. Strontium bromide is soluble. Silver chloride is insoluble because it has that silver in it. Sulfates are soluble, except those of calcium, strontium, barium, silver, and lead. These like exception elements, you'll notice that they're pretty standard, like the ones that are annoying are always going to be annoying. And that's okay, because at least they're consistent. So they're always going to be soluble. And now we move to our insoluble ionic compounds. The rule is that soluble rules always take precedent over insoluble rules. So hydroxides and sulfides are insoluble, except with group 1 ions, ammonium, and some exceptions, calcium, strontium, and barium. So magnesium hydroxide is going to be insoluble, but sodium hydroxide is going to be soluble because it's got that sodium in it. Carbonates and phosphates are insoluble, except when with group 1A ions and ammonium. So these are our solubility rules. So let's do an example. We're going to actually refer to the precipitation of lead iodine, which we saw in the video. Write the balanced chemical reaction and net ionic equation for the following reaction. Lead nitrate and potassium iodide forms what? I like to start by breaking up my compounds so I can see the individual ions. Now, I know that my cations and anions can switch partners. Because of this, precipitation reactions are commonly called double displacement reactions because both partners are displaced. Or if you're corny like Ms. Beglin, you're going to call it a square dance reaction. Because they switch partners like in a square dance. So we get potassium nitrate and lead iodide. How do we know what's soluble? How do we know what's insoluble? We consult our solubility rules. So, okay, I have potassium nitrate. Sorry, I'm pointing at it and you can't see me. I have potassium nitrate. Well, anything containing potassium and anything containing nitrate is soluble. So that is 100% going to be soluble. Lead iodide. Okay, anything containing iodine is soluble, except when paired with lead. This is going to be insoluble. Of course, we want to balance our equation, so there we go. So here's my chemical reaction. Now I want to write my net ionic equation. And I do that by getting rid of the spectator ions. So we have our potassium is still going to be aqueous. And our nitrate is still going to be aqueous. But our lead iodine is going to be solid. So that means that nitrate and potassium, those are our spectator ions because they're aqueous before, aqueous after. They didn't actually do anything. So my net ionic equation is Pb2 plus aqueous plus 2I minus aqueous forms solid lead iodide, which we can see precipitating here. All right, scholars, please take 4 minutes to write the balanced chemical reaction and net ionic equation for the following reaction. I'll set the timer and go away. Scholars, that's embarrassing. The timer stopped running. I have no idea how much time has passed. So we're gonna say 1 more minute, and I'm gonna set a timer on my phone. All right, scholars, let's stop there and let's go over this together. So, silver nitrate reacts with barium bromide. I'm so silly, that's not barium, that is sodium bromide, to do something. And we're gonna figure out what that something is. So we can do a little square dancing. Again, I really like to write out stuff as it exists in solutions dissociated because it helps me see their individual charges. And that's important when you're trying to figure out what compounds it forms. So we get sodium nitrate. And I know that that's aqueous because I know that anything containing sodium and anything containing nitrate is going to be soluble in water. And then my silver bromide react. All bromides are soluble except those containing silver. So this is going to be a solid. Here's my balanced chemical reaction. I get rid of these spectator ions. That way I can write my net ionic equation. And I get that aqueous silver plus aqueous bromide forms solid silver bromide. And that is all for today, scholars. I will see you next time.